Welcome back to Fun Facts Online. Today we are diving into a transformation that is fundamentally rewriting the rules of software engineering. For decades, we have treated codebases as static entities. We looked at them like archaeologists, digging through layers of commits and trying to decipher the cryptic messages left by developers who moved on years ago. We were trying to reconstruct the why behind the what. But that era is ending. We are moving from static analysis to what is known as repository intelligence. This is not just about an AI writing a function for you or fixing a syntax error. It is about an artificial intelligence that reads the entire biography of your software. It treats a repository not as a folder of files, but as a living, breathing neural network of historical decisions, architectural intents, and human relationships. By the end of this episode, you are going to understand the neural architectures like MergeBERT and graph neural networks that make this possible, how this technology is predicting technical debt before it happens, and the serious ethical minefields regarding surveillance and privacy that we have to navigate. Let's get right into the engineering. To understand repository intelligence, or RI, we have to look at how limited our tools used to be. Traditional static analysis tools, like linters or security scanners, were myopic. They suffered from static blindness. Imagine a proofreader who checks a single page of a novel for spelling errors, but has absolutely no idea about the plot holes or character development happening 3 chapters later. That was our tooling. Then came the first wave of generative AI, like the early GitHub Copilot. This was essentially autocomplete on steroids. It was trained on billions of lines of public code, but it was amnesiac. It didn't know your specific coding standards, and it had no concept of time. Repository intelligence bridges this gap by adding the fourth dimension, time. RI systems ingest the entire .git directory. They analyze commit history, pull request discussions, ticket tracking systems, and CI/CD logs. They build a mental model of the software's evolution. So how does a machine actually understand history? It relies on a sophisticated stack of vector databases and graph theory. At the heart of this is the concept of embeddings. Models like codebert or GraphCodeBERT convert snippets of code into high-dimensional vectors, which are essentially long lists of numbers that represent semantic meaning. In a traditional search, if you look for the word authentication, the computer matches that exact text string. But in a vector search, searching for authentication might return code labeled login user, verify token, and OAuth handler. The AI understands they are conceptually related, even if they don't share the same words. But RI takes this further with temporal embeddings. It doesn't just embed the current code, it embeds the diffs. If you write a commit message that says fix race condition in login, the system embeds that natural language intent alongside the actual code change. This links the human intent with the machine logic. The second pillar of this architecture is graph neural networks, or GNNs. Software is rarely linear. It is a graph of dependencies. Function A calls function B, which inherits from class C. RI tools build a massive knowledge graph, where nodes are functions, files, authors, and commits. The edges of the graph represent relationships like calls, defines, modified _by, or fixes _issue. GNNs traverse this graph to find hidden patterns. For example, if developer A often introduces bugs in module X, and developer B typically fixes them, the GNN learns a remediation relationship. It can literally suggest developer B as a reviewer for developer as pull requests automatically. Perhaps the most impressive technical breakthrough in this field is MergeBERT. Anyone who has worked in a team knows the pain of merge conflicts. Resolving them requires understanding the intent of 2 diverging branches. MergeBERT uses token-level 3-way differencing. It takes 3 inputs: the base version of the code, branch A, and branch B. It treats the merge conflict not as a text editing problem, but as a classification problem. For every conflicting chunk of code, it predicts: keep A, keep B, combine A then B, or synthesize new code. By training on millions of successful merges from open source projects, MergeBERT can resolve complex conflicts with over 65% accuracy, handling situations where lines were reordered or variable names changed, something standard Git algorithms simply cannot do. Now, let's move from architecture to application. How is this changing the daily life of a team? The first major application is what we call the debt detective. Technical debt is the silent killer of velocity. Usually, you only find it when it's too late. RI monitors code churn, areas of the codebase that are frequently edited. High churn usually indicates poorly understood requirements or brittle code, but RI goes beyond just flagging current debt. It forecasts future debt. It might warn you, saying, "Warning, you are adding a circular dependency between module A and module B. Historical data suggests this pattern leads to a 40% increase in bug reports within 6 months. That is a game changer. It shifts maintenance from reactive to predictive. Another massive application is automated archaeology and onboarding. Onboarding a new developer to a legacy codebase is notoriously expensive. With RI, a new developer can ask the agent, how does the refund logic work? The AI can respond with a historical context. The refund logic is handled in refund service, TS. It was originally synchronous, but was refactored in PR number 402 by Sarah to use a message queue because of timeouts during Black Friday 2024. This turns hours of investigation into seconds of retrieval. We also have to talk about security, specifically as a supply chain sentinel. Standard tools scan for known vulnerabilities, or CVEs. RI scans for anomalous behavior. It learns the patterns of the humans working on the project. For instance, it might flag a security concern by saying, developer account Mike usually commits code between 9 a.m. and 6 p.m., coordinated universal time from a London IP. A commit was just pushed at 3 a.m. from a totally new IP address, modifying a critical crypto library. This matches the signature of a compromised credential attack. This is behavioral analysis applied to code authorship. So what does a day in the life look like in this AI-augmented world? Imagine logging in at 8 a.m. Your AI daily stand-up summary is waiting. It doesn't just list commits. It narrates progress, telling you that the front-end team changed the data shape of the user object, which specifically affects your current task. By 11 a.m., you open a pull request. The AI reviewer runs instantly. It comments, you missed a null check on user.address. In incident number 902 last year, a similar omission caused a crash. Also, you are introducing a new dependency that conflicts with our lightweight client architecture decision recorded in ADR 004. Later, at 2 p.m., a production bug hits. You ask the RI, what changed in the last 24 hours that could affect login latency? The AI correlates a database migration merged yesterday with a slight increase in query time seen in the logs and suggests a rollback strategy. This isn't science fiction. These workflows are being built and deployed today. However, we cannot discuss this technology without addressing the dark side. With great power comes great peril. The same AI that helps you code can be used to control you. We are facing the potential rise of the panopticon of bossware. If the AI knows every commit, every pause in typing, and every bug you introduced, it creates the potential for invasive surveillance. Managers might be tempted to use AI productivity scores to rank employees, asking why Alice took 4 hours to write a function when the AI predicted it would take 30 minutes. This creates a chilling effect where developers stop taking risks or experimenting because they know every mistake is permanently recorded and analyzed by the optimality algorithm. Organizations must establish clear boundaries. RI should be used to empower teams, not to micromanage individuals. Then there is the issue of privacy and data leakage. We all remember the Samsung scenario in 2023 where employees leaked sensitive code into ChatGPT. With repository intelligence, the model lives inside the repo. If that model is hosted by a third-party vendor, does your proprietary algorithm effectively belong to them? There is also the risk of model inversion attacks, where hackers query an AI coding assistant to trick it into revealing secrets it learned during training, potentially autocomplete actual API keys or passwords found in config files. Furthermore, there is the risk of intellectual property contamination. If your internal AI model is fine-tuned on open-source code with restrictive licenses like GPL, and it suggests a block of code to your proprietary software, are you violating a license? The AI might strip the license header but reproduce the logic verbatim. This could expose companies to massive lawsuits. RI tools need reference checking features to flag when generated code mimics a known open-source source too closely. Finally, we have to look at bias in the machine. If an AI learns from history, and history contains bias, the AI will repeat it. If historical data shows that pull requests from junior female developers received more nitpicky comments than senior male developers, the AI might learn to replicate this strictness when reviewing code from certain accounts. Or, if a codebase has 10 years of bad security practices, the AI learns that this is just how we do things here and will suggest insecure code, reinforcing technical debt rather than solving it. Looking ahead to 2030, we are moving towards self-healing codebases. We will move from suggesting fixes to autonomous repair. An AI agent running in the background detects a dependency vulnerability, creates a new branch, updates the library, refactors the code to match the new API, runs the tests, fixes regressions, and merges the PR, all without human intervention. We will likely see a shift to AI-first repository structures. Currently, we structure code for humans with readable folders. In the future, we might include context files, meta-documentation, written specifically to help the AI understand business logic. The role of the developer is shifting. We are becoming the product owners of the AI. We define the intent and the constraints, and the repository intelligence handles the implementation. Repository intelligence represents a maturation of our relationship with software. We are moving away from the view of code as text to be edited toward code as knowledge to be managed. By granting AI deep access to our history, we unlock a level of productivity and insight that was previously impossible. But this transition requires a culture shift. We must learn to trust the machine as a partner, while verifying its output as a subordinate. We must guard against the misuse of data for surveillance. And we must ensure that as we hand over the history of our code to AI, we do not lose the human creativity that started the story in the first place. The repository of the future is not just a warehouse for code, it is a digital brain, and for the first time, it is beginning to think. Thanks for listening to Fun Facts Online.